Good morning, everyone. Good morning, ma'am. Um, Miss Aju and Miss Akas will be presenting today the clinical pharmacokinetics. Our agenda for today's discussion will be the plasma time curve, pharmacokinetic models, pharmacokinetic compartments, pharmacokinetic parameters, half-life, steady-state concentration, drug clearance, area under the curve, volume distribution, loading dose and priming dose interval, and elimination rate constant. For In our pharmacology, one of the foundation principles in pharmacology is that most drugs, the intensity of the effect on its related concentration at its sites of action. Because the greater the concentration, the more receptors are occupied. In this picture, we can see na may different types of receptors siya. So, it's a matter of yung parang i-assess, yung parang pairing po ang this picture representing. So, if bigger yung concentration niya, madaming receptors ang magkukuha din sa kanya. And this red picture here, yung square po, ay, not square, ay diamond, is ito po example is yung drug. The next one is pharmacokinetic. Pharmacokinetic is a study and a process of drug undergoes as it reaches to the site of action. So, in other words, we call it para easy natin ma-remember what the body does to the drug. And under po nito, yung LADME or yung pharmacokinetic process na liberation, absorption, metabolism, and excretion, and distribution. So, clinical pharmacokinetics, it is a study, of course, of the absorption, distribution, metabolism, and excretion. So, with the corresponding drugs and its pharmacological response. These clinical pharmacokinetics can be applied in our daily practices when it comes po sa mga therapeutic index po. Example po nito ng digoxin na may narrow therapeutic index. Sa small amount lang po niya, it may lead to toxic or therapeutic dose. So for this pharmacokinetic process, it started with the liberation, then next to the absorption, distribution, metabolism, and excretion. In this next picture, it will be easy for us to understand that liberation is something in how the drug is released. For the absorption, how the drug will get in. For the for distribution, where will the drug go? And for the metabolism, how it will be broken down. And for the elimination, how does it leave? So it is a guide question for us to understand what this pharmacokinetic process will be. So for the plasma time curve, it is the plasma time curve is generated by obtaining the drug concentration. And we all know in pharmacokinetics, the important part of it is the concentration because this drug concentration will be our baseline on how to measure on how we will determine to measure a specific drug. So by this, the plasma drug concentration versus time curve is most often used to measure the systemic bioavailability of a drug from a drug product. May definition of terms lang po ako i-represent. It's a, para po itong parang refresh na lang po para sa atin. So, the minimum effect concentration or MEC, it is the minimum concentration of the drug needed at the receptors to produce the desired pharmacological effect. So, ibig sabihin po nito, upon pag-take ng medicine, meron na pong minimal na upon pag-take na may minimal po na concentration na magpapass on po na to spread its pharmacological effect. The second was as a minimum toxic concentration of the MTC. It is a minimal concentration of the toxicity level. So the onset of time, it is the time required the drug to take its effect or its minimum effect concentration. Next one is the duration of action. So the duration of action is a onset of time and the time of the drug decline back to its minimum concentration. Ibig sabihin po nito is from start po na ininom po natin yung gamot, may corresponding hours po yan until babalik po siya sa kanyang reach po ang steady state, then magde-decline. Upon pattern, yan po yung decline, upon decline po, yan na po yung kung sa daily po natin iniinom na medicine, mga another dose na rin po tayo. Next one is the time of peak plasma level. It is the time of a maximum drug concentration in a plasma and an average rate of drug absorption. Ibig sabihin po nito is yung concentration po ng plasma levels po, marireach po yung max dose po niya. I'm not marireach. I mean yung time po kailan ma-reach yung maximum dose. For the peak plasma level naman po, it is the yung nare-reach po ng plasma concentration, yung maximum drug po. Kunwari, magdi-discuss ako later for the next slide. So, this related to the dose and the rate constant of absorption and elimination. So, for the area under the curve, ito ang usually amount of drug absorbed systematically. In this picture, meron, there is a corresponding hours. Example po, it's from 0 hours to 5, 10, 15, 20, 25, 30, 35. And yung plasma concentration po naman po is nasa milligram per liter. So, and we all know this concentration, hindi po siya yung parang consistent po. So, if you will graph it, from the starting 0, dahan-dahan po yung drug concentration aakyat until ma-reach po niya yung kanyang maximum concentration or peak concentration. And as time goes by, bababa at bababa po yan siya until ma-reach po niya yung longest time po. Until ang ganito pong graph naman po, it is a good example kung ano po yung medicine tinitake po natin until sa iinom tayo ng another dose po ng gamot. So the next one is the method of analysis of pharmacokinetic data. In these pharmacokinetic data models, ito po yung parang paradigm po niya para mas maintindihan po natin yung pharmacokinetic na upon discussion throughout sa session. Ang first one po, may tinatawag po na model approach and model independent approach. Under po sa model approach, it can be the compartment, physiological model, and distributed parameter model. And for the model of independent approach, it is a non-compartment analysis. This pharmacokinetic model provide a mathematical expression for the time course of a drug throughout the body. And by this, pharmacokinetic parameters is used more on po sa computation. So, example po dito ng compartment model, which is under po for model approach, it is may interpolate an experimental data. And so, ito ang commonly na ginagamit po on how we will compute the drug. So, example of it, may sub-classification po ang under compartment model. It can be the mammary model and catenary model. Next one is the physiological model. It's a matter of realistic picture of drug disposition. So, kung sa pathophysiology po natin, ito po yung dinadescribe po na from starting po ng blood circulation until papunta ng heart, yun po yung ano po ang process po ng mga pharmacokinetic process po. And when it comes po dito from example, from oxygenated blood, from the heart to the lungs, at kung ganun po na process. So example po nito is yung tissue of the liver, lungs, and kidney. The third one is the distributed parameter model. This model is more complex. Na-fuse po ito ng physiological model at saka sa compartmental model. Kaya po, based po sa kanyang definition po, ang mathematical equation at saka yung data concentration niya is medyo complicated po siya. For our
Okay, good afternoon, everyone. So, for the continuation of the discussion of Miss Akas, I will be discussing the pharmacokinetic compartment. So, let us first define what was the pharmacokinetic compartment. So, they are actually a conceptual framework that is being used in pharmacology and a pharmacokinetics, which to simplify the description of how drugs or substances move within the body over a time. It is also a it is also not necessarily a physical location in the body, but rather a mathematical representation that helps describe the behavior of the drugs. And these compartments can actually represent the different tissues, organs, or physiological spaces where the drug is distributed or being eliminated. In the pharmacokinetics, which we study how the body absorbs, distributes, or metabolizes and actually excretes the drugs. Well, they often divided into the different compartments to better understand the process that being occur. So our body is thought of as the series of interconnected compartments where the drug can be present. Next, please. So for the compartment modeling are divided into two categories. First one is the mammillary model. So it consists of a central compartment surrounded by the connected with peripheral or non-central compartment, and none of which are being connected with each other. So in the other term, um, sample of the mammillary models are the drugs that cannot be reabsorbed and again by the body. So like for instance, the NSAID, so it can be reabsorbed in the kidney that are potentially contributed to prolonged anti-inflammatory effect and as well as the analgesic effect. So most probably they are the lipophilic drugs, but they have distinct functions with each with the other compartments for examples of the mammillary model. Next, please. So for the another compartment modeling is the catenary model. So as it defined here, it have all the compartments arranged in chain with the connected in series only to the nearest neighbor. So this is how it looks like the catenary model. So it is a chain. Now for me I think catenary model these are the drugs or the medicines that will not be considered to reabsorb, and it will result for the excretions after its metabolism. Like for instance, our aspirin, so it will be absorbed by the organs such as our stomach and intestine, and once it will be in the bloodstream, and it will immediately excreted via kidney. So most of them are an example of the hydrophilic drugs. Next. So for the pharmacokinetic compartments, there are actually two models. So we have the one compartment model and also the two compartment model. So first is the one compartment model. So this model assumes that the entire body acts as a single compartment, and it simplifies the description of the drug distribution and elimination, but doesn't account for the complexities of the body's different tissues and organs. So here are the equation where the C or is the drug, it represents the drug concentration in the central compartment at the time, and for the initial drug concentration in the central compartment, and K represent the elimination rate constant, and T is for its time. Now, for this one compartment model, we need to consider the entire body is being treated as a single compartment, and the drug's distribution and elimination are described by a set of parameters. So we need to consider these parameters such as the absorption rate constant, the elimination rate constant, the volume of distribution, and its bioavailability. Also, we need also to consider we need to assume that the one compartment model, so and as well as the instantaneous and complete absorption of the drug into the bloodstream or the first order absorption. Also, we have to uniform the distribution of the drug throughout the body, and lastly, enable for us for the one compartment model, we need to eliminate occurs for the central from the central compartment. So another compartment is the two compartment model. So in this model, the body is being divided into the main compartments. So the central compartment, which typically representing the bloodstream, and the peripheral compartment, which represent the tissues and our organs. So these models provides the more accurate representation of the drug distribution and elimination, accounting for the initial rapid distribution of the drugs into the central compartment and subsequently distribution into its peripheral tissue. So these are the equations for the two compartment model. So where is represented as the dose of the initial amount of the drug, and the K12 is the rate of the constant from the central compartment to the peripheral compartment, and for the K21 is the rate constant from the peripheral compartment to the central compartment, and T represents which time. For the two compartment model, in this model, we have the following assumptions. So first is the drug distributes rapidly from the central compartment to peripheral compartments. And second one is we need to ensure that the elimination occur from both compartments. And lastly, we need that the distribution between the compartment is being described by the distribution rate constant, which represents our K12 and our K21 as given in the equation. Next would be our pharmacokinetic parameter. So what is a pharmacokinetic parameter? So these are the pharmacokinetic parameter are numerical values used to describe the processes that determine the time course of the drug concentration in the body after our drug administration. So these parameters provide insights into how drugs are absorbed, distributed, metabolized, and eliminated within our body. So here are the some key pharmacokinetics parameters such as our bioavailability of the drugs, the volume of distribution, the clearance, the half-life, the area under the curve, the elimination rate constant, the distribution rate constant, and the time to reach maximum concentration, the peak concentration, and the first pass metabolism as shown by the diagram given to us by Ms. Akas earlier. So for the definition of terms given to us, um, for bioavailability, it represents the fraction of the administered dose that reaches the systemic circulation unchanged after oral or non-intravenous administration. So actually, bioavailability, it takes into the account factor such as incomplete absorption and the first pass metabolism. So for the volume of distribution, it is actually the volume of distribution, a theoretical volume that describes how extensively the drug is being distributed in the body relative to its concentration in the bloodstream. Now, in this parameter, it actually provides the information about the apparent spaces in which the drug appears to be distributed in the different organs of our body. And for the clearance, um, it refers to the rate at which the drug is eliminated from the body, typically expressed as a volume of plasma cleared to the drug per unit time. Now, it also encompasses all the processes that remove the drugs from the body, such as for the metabolism and for the excretion of the drugs. So another parameter, we have the half-life. So for the half-life, it is a drug at the time for it takes for the concentration of the drug into the body to be reduced by the half. So actually it gives an indication of how long it takes for a drug to be eliminated from our body. And for the area under the curve, so it measures the total exposure of the drug over time, and it reflects the cumulative amount of the drug in the bloodstream and often used to compare the overall bioavailability and the elimination of the different drugs in our body. Now, for the elimination rate constant, so the elimination rate constant describes the rate at which the drug is eliminated from the body, and it is related to the half-life of the drug. Now, for the next parameters, we have here the time to reach maximum concentration. So for our Tmax, it is the time it takes for the drug to reach its maximum concentration in the bloodstream after its administration. So we have seen this earlier in the graph given to us a while ago. And for the peak of concentration, or the Cmax, is the highest concentration of the drug in the bloodstream after their administration. So lastly, for the parameter, for the drugs, it is for the drugs administered orally. So first pass metabolism occurs when the drug is metabolized by the liver before reaching the systemic circulation. So these significantly affect the drug's bioavailability. So for all these parameters, we will give you our different equations, each equations, and samples later on. So these parameters are being determined through the pharmacokinetic studies, all of them, and which will involve the collecting blood samples at a various time points and after the drug administration, and then using a mathematical modeling to calculate these values. So pharmacokinetic parameters also important for us to understand of how drugs behave in the body and to optimize the dosing regimens, predicting the drug interactions, and ensuring that the efficacy and the safety of our medications.
So the first parameter, pharmacokinetic parameter we will discuss is the half-life. So it's a time concentration of a drug in a plasma decreases by one half. So T one half is equals to the volume of distribution, or the volume over the clearance, which is the volume per time. So it will be multiplied by 0.697 or zero point 0.7. This is from the law of algorithms. If you will remember sa ating pharmacokinetics before. So the next one is the steady state concentration. This CSS, or the steady state concentration, is a time during which concentration of the drug in the body stays consistent. In this graph, we can see that upon the drug upon the person takes a drug and consistent po yung dose na iniinom niya with the right time if interval, marireach po mismo ng drug yung steady state concentration niya. And when it comes po sa pharmacological po na aspects, ito po ang gusto marireach ng mga physicians or healthcare providers so that matitreat ng maigi yung patient po natin. So for most drugs, the time reach of steady state is around 4 to 5 half of the lives. So in this graph, it is presented, di ba, na multiple of half time. So from 1, 2, 3, 4, 5, 6, and so on and so forth po siya. So for the steady state concentration is equals to the loading dose plus the IV infusion rate in millimeter po ito. So the next one is the drug clearance. So it is the rate to eliminate the drug. So drug clearance is equals to elimination rate over the remaining drug. So this clearance, the drug clearance is a baseline on how our kidney will filter it or works. So with a low clearance level, there is a low drug loss in the urine. If a high clearance level naman po, it, i- it, it is equivalent to the high drug loss in the urine. So for the area under the curve, it is directly related to the dose over the drug clearance. So if If our dose is high, there is a greater area under the curve. But if the greater the clearance, there is the smaller area of under the curve. If if we will um if we will compare it yung sa higher the dose, 'di ba ma-reach agad niya yung kung higher the dose pong ibibigay sa isang patient, mari um we all know mari-reach pa rin nila yung parang um Tmax or yung peak ay yung peak max concentration nila. Pero magdi-differ na lang po talaga yung sa doses at saka clearances po. And every time po may initake po yung isang patient. So, this is the example of area under the curve derivation. May mga problems po na depende po kasi sa problem if ma-encounter natin na ano po ang hinihingi nila. And this is an example of the derivation of the area under the curve.
Okay, so the next parameter is the volume of distribution. So for this equation, we'll be following the volume of distribution, the amount of dose of the drug in the body divided by the concentration of the drug in the plasma. So an example given here for the this is the simplest form of the volume of this for the solution for the VD or for the volume of distribution. So an example for a patient is administered a dose of 100 milligram of a drug after the drug has distributed throughout the body. So a blood sample is taken, the drug concentration in the plasma is found to be 10 milligram per liter. So using the formula, we can calculate the volume of this of distribution. So for the dose, we have the 100 milligram over the concentration of 10 milligram per DL, and we will be cancel out the milligram. So our result would be the 10 liter for the volume of distribution for this example. So next. So for the loading or priming dose, this equation, we have the target concentration times the volume of distribution. Now, an example for this solution or computation for the loading or priming dose, patient needs to achieve a target concentration of 20 milligram per liter for a specific medication, and the volume of the distribution is for this drug is 15 liter. Now we are actually looking for the loading dose or priming dose. Now we have here 20 milligram as the target concentration, and 15 liter for the volume of distribution. And this we just have to multiply 20 milligram per liter times the 15 liter, and we need to cancel out the liter. And we will have the result for the loading dose of 300 milligram. So this is for the sample of loading dose or the priming dose. Next, please. So for the dosing interval, so this is the equation for calculating the dose of interval. So dosing interval, we have the natural logarithm, the desired concentration, and the divided by the starting concentration over the elimination rate constant. Next, please. So for this example, if you have a drug with a half-life of 8 hours, so you want to maintain a constant therapeutic concentration of 20 milligram per liter, which is represent our desired concentration in the patient's body. And the concentration just before the next dose is the starting concentration, which represent the 40 milligram per liter. So in this scenario, we need first to calculate the elimination rate constant because it was not given. So first, we have to get the elimination rate constant. We need to have the natural log of 2 divided the half-life, which is 8. Now, the result for the elimination rate constant will be 0.0866 per hour. Now, since we have already our elimination rate constant, we can now actually solve for the dosing interval. Now, in this, we need to get the desired concentration and the starting concentration. So we have 20 milligram per liter and for the desired concentration and its starting concentration, which is 40 milligram per liter, divided by the elimination rate constant, which represent 0.0866 per hour. Now, first is we need to divide the 20 milligram per liter divided by 40 milligram per liter, which results to the zero point 0.5. And then we need to get the log of zero point 0.5, which the result is 0.6931 divided by the elimination rate constant, which is 0.0866 per hour. And our dosing interval will be 8 hours. Next, please. And lastly, for the elimination rate constant, this is the equation we have. So we have the C that represents the drug concentration in the body at the time, and the initial drug concentration at the time, and K represent the elimination rate constant, T1 which represent the later time, and T2 is the starter time. Next please, ma'am. So for an example of this elimination rate constant, if you have a drug with a known half-life of 6 hours and you have observed a decrease in drug concentration from 80 milligram to 20 milligram per liter over this time period, so to calculate this elimination rate constant, we can use this formula. So we need to transpose. So 80 milligram, which represent our um, concentration at time, and 20 milligram per liter, which represent the concentration at time 2. So for the T2, we have the 6 hours, and for the T1 is the 0 hours because this is our starting time. Now, we need to transpose. So, we have 80 divided by 20 milligram per liter. We have 4. And it's 6 minus 0, we have 6 hours. And we have to get the log of 4. We have the result of 0.6931 divided by 6 hours. And our elimination rate constant is 0.1155 per hour. So this is the example of the solutions for our elimination rate constant. So that would be all. Thank you.
Thank you po.
Thank you. Do you have questions uh, for the reporters? You may ask question if you have. Unmute nyo lang ha. Wait lang ha. A minute. It should be introduction. If ever wala, I'll just add kung ano na yung na-discuss ng mga reporters. I have already uploaded these slides kasi dalawa ito. Yung compartment nasa week 2 and then ito nasa week 3. So this is still actually under the introduction for our pharmacokinetics. So syempre, we all know what pharmacokinetics is. In our undergraduate na studies, we knew that when you say pharmacokinetics, it is what the body does to the drug. Okay, so in the study of pharmacokinetics, we have a lot of roles here, and that is actually to ensure that we give correct drug treatment to our patients. And when we say correct drug treatment, that includes, syempre, the correct drug, and then the correct dose or the concentration, and then syempre yung kung multiple dosing ito, the interval, the dosing interval. And we have to actually understand the condition of the patient for us to really ensure that we give the correct drug treatment. We have to check also the pharmacology of the drug, its action, the pharmacodynamics included. Um, and then we have to ensure also na we will not be reaching the toxic level of these drugs or drug in the body. Okay, so when we are going to perform a pharmacokinetic study, we have syempre the preclinical trial wherein we give or we do experiments with laboratory animals to check and identify the correct dose of the drug. And then after that, we may do testings also syempre sa human. How are we going to do that? We collect samples like the blood. Most of the time, it's the blood for us to determine the plasma concentration of the drug. Or pwede din naman sa urine, sa bile, sa feces if we want to know like the rate of the elimination or the excretion of the drugs inside the body. So we do this in various time points. And then once we have collected samples, we analyze these samples for the presence of drugs or their metabolites. And then we analyze the data. And then that's how we come up with the pharmacokinetic profile of our drugs. So again, when you say pharmacokinetics, um, it's what the body does to the drug, and we revolve around the four principles: the absorption, distribution, metabolism, and excretion of these drugs. When we apply these pharmacokinetic principles in making sure that we give the correct drug and everything about the drug sa pag-treat ng ating patient, we call that clinical pharmacokinetics. Okay? So, ito yung study natin sa pharmacokinetics and as well as the pharmacodynamics. So, sa pharmacokinetics, again, we have absorption, distribution, and elimination. So, when you say elimination, that includes metabolism and excretion. Now, if we want to study the effect, the response of the body to the drug, then that will be under the pharmacodynamics. Okay? So, before that, let's talk first about the pharmacokinetics. Let me just change kasi nakahiwala yung aking slide. Wait lang. So this will just be quick. And then after that, you may do the uploaded activities in the Google Classroom. Okay. Nangyari. Just tell me if hindi makita yung slide ha. So we have here the pharmacokinetic compartment. So when you say compartment, this is a concept, a mathematical concept we use to describe a part or a portion of our body in which the drug most likely will occupy after the administration. So it does not really need to correspond to any a specific anatomical space or physiologic volume. So ano lang yun siya, concept, mathematical concept that we use, or hypothetical structure inside our body used to describe where the drug is already after the administration. Okay? So we use these models to predict the time course of drug concentrations in the body accurately. And then the selection of these compartment models depend on the distribution characteristics of our drug, again, after administration. Now, a rapid na distribution would suggest that the rate of transfer of the drug from the bloodstream after the absorption to all organs and the tissues back into the blood have become equal instantaneously. So again, that's following drug administration. If slow naman ang drug distribution, then that would mean we have greater number of compartments. So yan yung nire-represent ng ating mga compartment models. The more you have compartments, meaning yan, slower yung distribution ng drug from the blood to the tissues or organs in the body. So we have different or various compartment models na ginagamit sa pharmacokinetic study. So when you say one compartment model, the body is treated as one unit only. So this one assumes that after administration, the drug is evenly distributed all over the body. So itong model na ito, the one compartment model, is to be used if the drug is rapidly and at the same time readily distributed between the blood or the plasma and the other tissues in the body. However, if the blood does not really readily distribute from the blood to the tissues in the body, then we may use the two compartment or the multi-compartment model. So for the two compartment model, we have here a central compartment and a peripheral compartment. So the drugs, we will have different rates here sa distribution. So like from the compartment model going into the peripheral model, yung pag-distribute ng drug from the compartment, from the central to the peripheral and from the peripheral to the central until we get to have like a state of equilibrium between these compartments. So for the multi-compartment model, the drug syempre will distribute to a lot more than one compartments, and then we will have lots of rates also of drug distribution here, as well as like lots of rates of excretion or elimination of the drug. Now we also have the so-called non-compartmental pharmacokinetics. So we do this if it is not really appropriate for us to use either the single or the one compartment or even the two compartment, or lastly yung multi-compartment model. So when do we use this non-compartmental pharmacokinetics? So number one, if clearance is organ independent, or if the elimination does not occur solely from the central compartment. So again, si non-compartmental pharmacokinetics is dependent on the clearance of the drug. If we don't really excrete the drug in one organ only, or hindi siya na-eliminate in one central compartment, then hindi tayo makakapag-gamit ng compartment models din natin. Okay? So this is totally dependent sa total drug being administered to the patient. So, ang ginagamit dito for the study is the area under the curve, or the AUC. So, it is expressed as the total amount of drug that reaches the bloodstream after the administration. And yung calculation of the area under the curve for this non-compartmental pharmacokinetic follows the trapezoidal rule. So, ito yung mga examples. We have here the one compartment model. So as you can see, we only have one compartment. Here, the body is being treated as one unit. So like if the drug is being administered, the drug is evenly distributed all over the body, and we have one elimination constant only. Okay? May question ba? Wala. You just send your questions if ever you are unable to turn on your microphone. Just send your questions. sa chat box. I'll answer that later since I cannot see the questions or the chat box if I present my PowerPoint presentation. And then we have two compartment model here. So we have here the number one is treated as the central compartment, and that the drug will be distributed to another compartment, which is like another tissue or another organ in the body. So we have like different rates here, rate of the distribution from the central to the peripheral, and another rate of the distribution of drug from the peripheral to the central. And we have here the K10 is, or the K10 is actually the rate elimination constant after the distribution of the drug. So itong three compartment model may also be called as multi-compartment. So we have more than one here. We have the central. We still have the central compartment. However, the drugs are distributed to a lot of tissues in the body. So like we have different tissue here that is represented by number 2, and then another tissue here for the number 3 na compartment. So if we are going to do pharmacokinetic study on this, then we will have to compute for a lot of rate of distribution, and even we still have also here the rate of elimination. So as you can see, the elimination for the 1, the 2, and the 3 compartment models take place in the central compartment. Kapag ka hindi nangyayari dyan yung elimination ng drug sa central compartment, that's the time we need to use this non-compartmental pharmacokinetics. So, yung compartment selection process, kung ano yung gagamitin natin, single ba or one, two, or multiple, or non-compartment pharmacokinetic model. This one, ito yung magaguide sa atin. So number 1, the physicochemical properties of a drug, or the frequency of the plasma samples collected, and even the sensitivity of the procedure employed to analyze drug concentration in plasma sample. So ito, ano lang ito, parang visual representation. So ito ulit yung one compartment. So like it's a one unit. So if you're going to administer a drug, then the drug will be evenly distributed all over the body. Now, on the right, we have the two compartment model. So like this one, we have the central here on the left, and then the peripheral on the right. And then if we are going to administer the drug, for example, from the central compartment, the drug will move into the peripheral compartment, and vice versa until we get to reach an equilibrium. Okay, so that's two compartment model. So this is another one for one compartment. Again, the drug after administration will be homogeneously distributed all over the body. And then for the two compartment model, so we have here before administration, and then after administration, the drug will slowly be distributed to the different organs of the body. So kaya meron tayong second compartment until like magpapasa-pasa yung drug between these organs, so treated as the second compartment and then the central compartment, until we will reach the equilibrium. Okay, so the body will have drugs, okay, all over. So that's two compartment model. This is just another representation though, but parehas lang naman din yung nire-represent nitong representation ng one or two compartment model. So merong distribution, merong redistribution. Now how about yung plasma concentration? So ito yung if we yung sa graph na yan, syempre you have the concentration, like at 0 time, that's the time na mag-a-administer ka pa lang. And then you have here the time, kung ilan na yung drugs na umabot or natira sa plasma. So we have the solid line represents there the serum concentration for a drug that follows one compartment pharmacokinetics. So this one is for a drug administered IV bolus. Now, yung dashed dyan, yan naman yung serum concentration for a two-compartment model. So, kung sa one compartment, diretso-diretso lang yung kanyang pagbaba. This one here ay yung nasa green. Kasi nga, we have our body as one unit only. So, constant yung pag-eliminate then after that distribution. However, that is not true for a two-compartment model since the drug will be distributed first to another tissue or another organ before it gets eliminated. So, that's for the compartment model. Do you have questions or like clarifications before we'll continue with this one? Wala. So ito, let's continue with our pharmacokinetic na mga parameters. Okay, so we are done with our compartments. So the first one here is the plasma concentration time curve. So what will happen to our drug if taken orally or if taken through other routes of administration? So we have here a curve that will represent that. So like at a zero time, syempre, the drug is yet to be administered. And then the graph will most likely pagpataas yung kanyang yung kanyang path if umabot na siya sa blood natin. So, we have here plasma concentration until ma-reach niya yung Cmax. So, this has been defined by the reporters a while ago. So, the maximum concentration after administration, that's the Cmax. And then the time when we reach that maximum concentration in the plasma after the administration is the Tmax. So that is still on the absorption phase here. Now kung after the Cmax, syempre bababa na yan siya and the drug will enter the elimination phase. So all the areas here under the curve represents the amount of drug that reaches the bloodstream after the administration. Okay? So ito, this is just a comparison of the area under curve of actually that is cocaine through various routes of administration. So this is intravenous. Syempre, you will really reach the Cmax here in a shortest time possible since syempre in-administer directly to the vein yung drug. And however, that is not true sa ibang routes of administration. So, just like this one, ang color niyan, the green one is smoked. Though, even though smoked siya, no, the drug will still reach the blood. However, it will not really reach the Cmax. Syempre maraming nangyayaring hindi lahat ng drug na-absorb. So nakadepende yan siya sa physicochemical property of the drug. Meron pa tayong, especially for orally taken, meron pa tayong mga first pass effect. Kaya hindi nga natin marireach yung talagang Cmax compared sa intravenous na injection. Okay, so the delayed peaks for these other types of administration means slower ang rate of absorption. So kapag nagsa-study tayo ng itong plasma time curve, marami tayong dapat i-consider. So like the number and scheduling of time points kung kailan tayo magdodraw ng blood from our sample from our patient, and then kung ilang beses tayo magdodraw ng blood para ma-check kung gaano nakarami yung dugo sa plasma. So we have here number of points. It is actually suggested na meron tayong at least 15. So the first 5 points before we get to achieve the Tmax, and then the second 5 points will be between the Tmax and the T1 half or the half-life, and the last 5 points are between the half-life and the 5 times the half-life. So yan yung mga points wherein we need to draw blood after the administration to really check yung plasma concentration of the drug inside the body, and then para meron tayong accurate din na plasma time curve. Okay? Pero if ever there is restriction in blood sampling, then we may instead use four time points. Okay? And then, ito yung single versus multiple dosing. So, yung nasa taas na graph, syempre, this is the single dose. So, we assume that on the time zero, there is no drug yet in the body. So, after administration, tataas hanggang aabot sa concentration, maximum concentration. Then, after that, there will be the elimination. Okay? Pero if multiple dose ang gagamitin natin, syempre we have second and subsequent doses for this, and that is actually to maintain a certain plasma level of the drug inside the body. So as you can see here, we have different peaks, a lot of peaks here that would represent the different doses of the drug being administered to the patient. So mostly na mga therapeutic agents natin are actually administered as multi-dose at a finite time intervals to really achieve a desired plasma level of the drugs. Okay? So, diretso lang ako ha, since this has been defined by the reporters a while ago. So, yung elimination half-life or the half-life, it's the amount or it's the time wherein the drug, half of the drug is being eliminated and then the other one stays inside the body. So, the longer the half-life, the longer the time where the drug is being eliminated in the body. And this is very important for the dosing interval, for us to know the when are we going to achieve the steady state concentration of the drug and when the drug is being eliminated in the body. Since for example that the patient has renal problem, then that would the half-life will really be affected. So pwedeng ma-prolong yung ating half-life. So you may use this formula. 697 ata yung gamit ng reporter kanina. However, it's okay. Decimal lang naman yung magkakaiba dyan. Anyway, half-life is equal to 0.693 over K. K is the elimination rate constant. Or you may use the other formula, 0.693 times the V. V is volume of distribution and the CL is the clearance. So this is how we are going to use the half-life in determining when are we going to achieve the steady state concentration. So as you can see on the graph, so we have here the first half-life, you will achieve 50% of the target na steady state concentration. And it will actually take 5 half-lives before you at least reach 97% of the steady state concentration. So kung alam natin yung half-life ng drug, ma-determine natin anong oras din natin maa-achieve yung steady state concentration natin. When you say steady state concentration, that's actually yung rate of input or the rate ng in-administer na drug, the drug na umabot sa bloodstream is equal to the rate of output, meaning equal din yung rate of elimination of the drug. Now, for the clearance, it's the volume of the blood or the plasma being cleared of the drug per unit time. If we want to compute for the clearance of the drug, we may use this one. Clearance can be equal to elimination rate of the drug in milligrams per hour over the concentration. That's milligram per liter. So, ano yan siya? Pwede din ito. Clearance is equal to the volume of distribution times the elimination rate constant. Or you may tawag dyan sa mathematics, i-derive niyo yung formula. Like we have here, if you want to compute for the elimination rate constant, it's the clearance divided by the volume of distribution. Now, when you say volume of distribution, this is not actually a physiological parameter. We use this one just to represent the fluid in the body where we assume na the drug is being distributed. So, after the administration, the absorption, we assume na itong mga drugs na ito ma-distribute either like sa plasma or sa interstitial fluid or sa loob ng cell, intracellular fluid. So approximately that will be a total of 42 liters lahat-lahat ng fluids natin na tinitake into consideration for the volume of distribution. So how do we compute our volume of distribution? You just need here the dose in milligrams divided by the plasma concentration. Okay, so that's in milligrams per liter. So you will have liters as your unit here for the volume of distribution. So what is the implication of this? After computing, if you get a low volume of distribution, that means there is a decreased tissue binding, hindi masyadong umabot sa like tissues yung drug natin, and that the drug most likely stays in the plasma, and in the plasma we have the so-called protein binding, so most likely nandoon yung drugs natin. At pag hindi siya na-distribute, most likely hindi din siya magkakaroon ng effect. Now, if we have a drug and then we compute the volume of distribution and we get a high volume of distribution, that means less ang protein binding and the drug most likely umabot doon sa tissues, okay, sa target tissues natin. So ito yung magiging guide natin. If we get to have a volume of distribution of at least like 4 liters and below, most likely the drug stays in the plasma, in the blood. So most likely may mataas yung protein binding. And then nasa interstitial fluid yung drug if you get at least like 5 to 10. And then more than that, ito yung nasa loob na talaga ng cell yung ating drug, intracellular fluid. So yan yung sinasabing if you get a high volume of distribution, most likely the drug has already gone to the tissues. Okay, and most likely magkakaroon siya ng effect. Kasi naabot natin yung target tissues natin. So this one is just an example na computation. Example, you have here the drug. The dose being administered is 100 milligrams. Now, after some time, nagkuha tayo ng concentration sa plasma, and the concentration of the drug in the plasma for the scenario 1 is 100 milligrams per liter. So, if magko-compute tayo ng volume of distribution distribution is equal to dose divided by the concentration. So that's 100 divided by 100. So the volume of distribution for the scenario 1 is 1 liter. And let's compare that to the scenario 2. We have the same amount of drug here. The dose is still 100 milligrams. But after taking a plasma sample, the concentration is just 1 milligram per liter. So bumaba yung plasma concentration. Now, how about the volume of distribution? So that's 100 divided by 1. The volume of distribution is 100 liters. So as you can see, the volume of distribution here in the scenario 2 is much, much higher. And that would mean the drug is out from the blood, meaning nasa tissues na siya. Okay, yung isa, nagstay pa sa blood. Okay, questions or clarifications? Ay, hindi makita ang graph. Anong graph ito? Sorry, ngayon ko lang napansin yung chat. Tell me ha, ngayon makita na, hindi ko na lang siguro siya ipalaki, no? Pwede ba siguro ganyan lang siya? So, ito, this one is an example So, wait lang. So if 3 gram of drug is being administered or added and distributed in a tank, the resulting concentration is 0.15 grams per liter. So calculate the volume of the tank. So this is an example of a computation of the volume of distribution. So this is the dose here and this is the plasma concentration. So 3 grams divided by 0.15 grams per liter, the volume of distribution is 20 liters. And if you're going to look at that, most likely, kung 20 liters siya sa body, nasa intracellular fluid na siya. Okay? So another parameter here, no, this is still the volume of distribution. Meron kasing mga scenario na the volume of distribution is being given and ano siya, naka-liters per kilogram siya. So for you to get the real volume of distribution, just multiply it sa weight ng ating patient. So just like this one, for a 20-year-old female that weighs 60 kilograms, the gentamicin supposedly 0.25 liters per kilogram yung volume of distribution. So, i-multiply natin siya sa weight niya. And then, the volume of distribution of the gentamicin is 15 liters. So, yan yung example. And then, this one naman is for the loading dose. So, syempre, the loading dose is the initial dose we give to our patient, and our main goal, our main purpose is to just reach the steady state concentration quickly. Okay? So yan yung reason why we give loading doses. So this is used actually for drugs with a long elimination half-life. Para again, ma-achieve natin agad yung steady state concentration. So examples of drugs na merong mga initial or first dose or loading dose, itong digoxin, the teicoplanin, and the amiodarone. Okay, now how do we compute for the loading dose? We may use this formula. V is equal to D. The D there is the loading dose, and then the F is the factor. Actually, wala ba siya dito? This is the loading dose, yeah. And then the S is the salt factor. If meron siyang salt, so may mga drugs tayong nakasalt, so like 80% yung drug and then the 20% is the salt. So 0.8 yung factor niyan. And then divided by the concentration. So the target concentration minus the measured concentration. Okay? This one, nasaag ang ako ang, this should be here. This is for the dosing interval. Okay? So, sa dosing interval naman, syempre ito yung mga drugs natin na to be given in multiple dosing. So, we can also compute kailan yung magiging next dose natin using this formula. F is still the factor and then S is still the salt factor if ever meron ha. And then times the dose divided by the clearance times the steady state concentration. So we have to know first the bioavailability of the drug or the amount of drug that reaches the bloodstream. Or we have to know the fraction, the F, refers to the fraction of the administered dose that enters the systematic circulation. If 0 yung ating F dyan, yung fraction natin or yung factor, 0 means no bioavailability. Walang drug na napunta sa bloodstream after administration. Or for an intravenously given drug, the fraction or the F there should be 1 since diretso nga siya sa veins. Okay? So we have here an example. We would like to give orally 500 milligrams of tablet to our patient suffering from arthritis. So at what interval that the patient should take a dose? So use the following information in the calculation of the interval. So the F here, it's the bioavailability fraction is 0.7. That's the amount of the drug that reaches the bloodstream. And then for this drug para sa arthritis, the salt factor is 1. Now the desired steady state concentration is 10 milligrams per liter, and this drug is eliminated 6 liters per hour. So we are just going to substitute all this information here in our formula. The F again is 0.7, our S is 1, our dose given is 500 milligrams, divided by the clearance, that's 6, and then times the steady state concentration, which is 10. If we do the math, we have here 5.8 hours, or pwede siyang i-round off. So the interval for this 500 milligram tablet for the patient merong arthritis is every 6 hours. Okay, so yan yung pwede natin gamitin na formula. And then lastly, ito yung iba pang formula na pwede natin gamitin in the computation of the clearance. We have here the clearance. We just need the volume of distribution times the elimination rate constant. And then, this is for the elimination rate constant. So this is just a derived formula. Okay, so if we want to compute for the clearance also, but what we have is the half-life, then we may use this formula, 0.693 times the volume of distribution divided by the half-life. Now, if we want to compute for the elimination rate constant, we have here the formula 0.693 divided by the half-life. Or pwede ding kabaliktaran if we want to compute for the half-life. I-derive na lang yung formula. Now, pwede nating i-merge if you want to compute for the half-life, and what we have is the clearance. Ito yung gamitin. 0.693 times the volume of distribution divided by the clearance. So, take note, a decrease in our clearance due to like problems in the liver or the kidney will increase the half-life of the drug. So, yun yung compartments and mga parameters natin na ginagamit sa pharmacokinetics. And that is very important for us to know, number one, how much drug are we going to give our patient after, syempre, the diagnosis of the physician, and then determining that the correct drug to be given. So for the dose, or anong kailangang ibigay, single dose lang ba or multiple dosing tayo? So kung may multiple dosing tayo, kailan natin ibibigay yung next dose for our dosing interval. So a lot of parameters can be taken into consideration, like the volume of distribution, the half-life, the target concentration, or our steady state concentration. Now, do you have questions or clarifications? Pwede niya i-send kay mag-share screen ako. How do I do this? Wait lang. Not the window. I think it's the tab. Share. Ayan. So, I don't know if parehas tayo ng mukha sa Google Classroom, but I have already uploaded there the rubrics that is just for to be used sa pag-grade sa reporting. Ayan. And then yung sa week 1 na synchronous class, I have completed this also. I have provided there the YouTube video, and then yung mga hindi pa nakasagot nito kasi kaka-add lang sa subject, it's okay. Ay, naka-review siya. Pwede kayong mag-turn in kasi may 5 pang hindi nakakapasa. So, in your free time, you may do that. Yung sa abstraction, that is just the PowerPoint presentation I used last time during the introduction. And then, you may also start doing this. This is just one question. So, you may answer this for our remaining time since supposedly mag-end tayo ng 6:30. And then ito, since I think I need to complete even the asynchronous class of the week 2, I have also uploaded here a video. You may, again, look at this in your free time. And then I only have one question also. Actually, sa September 9 pa ang deadline nito. But anyway, You may do that in your free time. And then I have also included a copy of the PowerPoint presentation a while ago for the pharmacokinetic profile. And then another one here for the application. So this is just one case with three questions. So next week pa naman, yung i-accomplish natin ngayon yung sa week 3 na lang since hahabulin lang natin yung week 2. So sa week 3, yung activity actually yung ilalagay ko lang dyan. Since this one is being recorded, I'll give you a copy of the recording para ma-review ninyo if ever paputol-putol kayo sa reporting a while ago. And then you may answer the analysis. Again, this is just one question. For the abstraction, the abstraction kasi like is a supplement of the knowledge na alam nyo na. So as a supplement, I'll just give you a copy of the PowerPoint I presented a while ago. However, the reporter may also upload their PowerPoint presentation sa stream na lang doon sa klase sa dito. Dito nyo na lang siya ilagay. Okay? And then, this one is for the application. So, yung sa application natin na part, ano lang ito, problem solving. So, you may do this one. You have to show your solution and then round off your final answers to the nearest 100. So, ano lang siya. Practice problems lang ito. You may use the formula I have given you sa PPT. Okay? Sige, any other question or clarification? Hindi pa ako nalagay post. And anyway, wala nang question. Sure na talaga. We will have also like problem solving sa exam. Pero dili po tong, hindi yung mga super mahirap na. Let's just practice how to use this formula, yung volume of distribution, the half-life, the steady state concentration, yung loading dose, and the time interval. Yun lang naman.